mu nu omega mu nu. So can you quickly get to the calculator? E raised for so we have done this thing. Covariance of Dirac equation implies, so you can construct the psi prime x prime as s acting on psi of x, where this s we know it's now equal to either 4 sigma mu nu omega. Clear? Got it? Okay. So let's check the properties of individual transformations. Since this S contains both rotationals as well as boosters, because it is a complete Lorentz transformation involving rotations as well as boosters, so let's consider separately. So if I take let's say the rotations, and we know this S is unitary. Clear?
Yes, sir.
And this is a unitary matrix we have constructed, and this is actually unitary. Okay, so let's consider individual transformations and check whether those individual transformations are unitary or not. Okay, so let's take first the rotations. Okay, so just understand these things. These will be later on once we will do the irreducible representations of Lorentz group. So they will be useful here. We will see actually. You will be having two types of signals and they are connected by Dirac equation. So we'll get that kind of identification later on. For the time being, we are just looking at the properties of these objects, what we have arrived or derived from the covariance of Dirac equation. Okay, so just from the relativistic mechanics viewpoint, then we'll interpret them in detail what exactly these things mean. Okay, so let's take the rotations. In case of rotation, I am having this only omega ij, and I is equal to 1, 2, 3. Ij are simply what? 1, 2, 3. Clear? So for rotations, I am having only these are the parameters. Omega, let's say omega 1, 2, omega 2, 3, and omega 3, 1. Clear? So these are the parameters, which implies therefore I am having this. Let's write SR to be the matrix or the operator corresponding to the rotation. How it looks like that? E raised for minus I by 4. I will write simply sigma ij omega ij sigma ji omega gi. Is it clear?
Yes.
Okay, so what that will, okay, so let me write sigma ji omega gi. So how much is that? It is simply e raised for minus I by 2 sigma ij omega ij, because this is same as this thing. Clear? Got it? So you can, okay, so if you are not able to understand this thing, let's take your hand. This is sigma 1 2 omega 1 2. Then what is the another term? Sigma 2 1 omega 2 1. Clear? Got it? So that means the sum of these two will cancel a factor of 2 here. That's why it is I by 4. I have put, you could have put I by 2 directly. Okay. Then I by 2, you can see once we will calculate the spin of the matrix, it is sigma by 2. That will give you the spin of the particle. Clear? Okay. So now let's write the dagger of this thing. Let's take S dagger R. So how much is that? So it is e raised for I by 2, okay, sigma dagger ij omega ij. Clear?
Yes, sir.
Is it? Omegas are the parameters and you are in sigma dagger ij. Now can you tell me what is sigma dagger ij? Let's calculate that. What is sigma ij? So it is I by 2 gamma I. Okay, so let me write this. Sigma ij gamma I gamma j minus gamma j gamma I. Okay, so take its dagger sigma ij. Let's take its dagger. So it's minus I by 2. So what is when you take a dagger? So if they will get interchanged, sigma j dagger sigma I dagger minus sigma I dagger sigma j dagger. And you know, ith component of the gamma matrix is anti-Hermitian, is it? Gamma 0 is Hermitian, gamma I are anti-Hermitian. So this is equal to minus gamma j, this is equal to minus gamma I. So minus and minus is plus. Clear? Okay. So you are having simply minus I by 2. So you will be having gamma j, gamma I, minus gamma I, gamma j. So you can take minus inside. So it will be simply I by 2, gamma I, gamma j minus gamma j, gamma I dash equal to sigma I j. So that means special components of this matrix are Hermitian. Clear? If you take the entire 4 by 4 matrix, I mean the entire matrix containing all the 0 components as well, then it's anti-Hermitian. Okay? Got it? Okay. So therefore I can write this object as simply as e raised for I by 2 sigma ij omega I. Can I write it in this fashion? E raised for minus I by 2 sigma ij omega ij raised for minus 1. Can I write it? Huh? Because this minus 1 and minus will become plus. It's e raised for ax, that I will write as e raised for minus ax raised for minus 1. Clear? Okay, can I write it? Now tell me what this object is. E raised for minus half. It's SR. So that is simply SR. So raised for minus 1. So what does it mean? When you are having a matrix, U dagger is equal to U inverse. What you call that? A unitary matrix. Clear? So that means this SR is a unitary matrix. Since you are having S dagger equal to SR inverse implies SR is. You know, rotation matrices are what? Unitary matrices. Clear? So because I have considered only the rotations of the Lorentz group, Lorentz transformation. I am not considering group theory yet, but I am considering only the rotations. Okay? Now let's take the boosters. Okay. Now let's consider boost separately. So for that matter, I am having simply omega 0 I, and I is 1, 2, 3. Clear? So these are the parameters corresponding to boosters. So let me write that as, since these are Lorentz boosters, let me call it as SL. Okay? SL means the transformation matrix which induce a boost in a given signal. Okay? So how much is that? So it's e raised for minus I by 4 sigma 0 I omega 0 I plus sigma I 0 omega I 0. Clear? So that is simply equal to e raised for minus half sigma 0 I omega 0 I. Clear? Because this is same as this thing. Why? So you can interchange this I and 0, it will yield minus. This will also yield minus, minus and minus plus. Clear? Okay. So now let's take this SL dagger. Okay. So how much is that? So it is e raised for I by 2. Okay. Sigma 0 I dagger omega 0 I. Clear? So why this dagger is not affecting these omegas? These are real parameters, sir. Okay?
Yes, sir.
Let's say here it is velocity in the ith direction. Omega 0 I will be simply v by c. Let's say vi by c. Velocity in the ith direction. What about omega ij? It will be simply the angle in the given plane. Let's say omega 1, 2 will give the angles in the xy plane. Omega 2, 3 in the yz plane and so on. Clear? Okay. So now let's take this dagger of this thing. So what is omega's sigma 0 I? It's minus I by, we have calculated actually sigma 0 I in the last lecture. How much is that? Anybody remember? It's alpha, sorry, I times alpha I.
Yes, sir.
Or minus.
Plus.
It's plus, okay? So now let's take this dagger, sigma 0 I dagger. How much is that? It's minus I alpha I dagger. What is alpha? Alpha is a Hermitian matrix. So it's minus I alpha. Clear? Got it? So that means this very object is e raised power I by 2. So it is minus I alpha I omega 0 I. So how much is that? E raised power alpha I by 2, okay, omega 0 I. Okay? So if you see, so this is not equal to SL inverse. Okay, if I put, let's say, minus here, then take a minus. So, but you are having an I factor here, eh? So you cannot do it, eh?
Yes.
Got it? So, okay, so let me write it in that fashion. So you can write it as e raised power minus alpha I by 2 omega 0 I raised power minus 1, is it? But if you see in the original, there is an I, is it? So you don't have an I here, so that's not equal to SL inverse. It means Lorentz boosts, they do not form actually the unitary transformation. They are not actually unitary transformations. Clear? So how to make it as a unit? But we have seen actually S we have constructed for the boosters as well as rotation. That's the unitary matrix. So as a collective thing, it's a unitary transformation. As an individual thing, it's not a unitary transformation. Clear? Got it? Okay, so how to make it? Huh? How to put make a general definition for this unitary transformation? Okay. So gamma 0 comes at the rescue. Okay. So you got the point? Okay. So let's take this object, this gamma 0. Let's write this thing. Okay. So let's take gamma 0, okay, S dagger L and gamma 0. Let's multiply this S dagger L by gamma 0 on both sides. Eh? So this, how much is that? So that is gamma 0. What is SL dagger? Tell me. SL dagger we have calculated just now.
Yes,
it's e raised power
alpha I by 2.
Okay, L minus.
Plus.
So no. So we have an error somewhere. This is a minus sign. Sorry. So this is a minus here. Okay. So this should be a minus. So you need to check it. So it is to be a minus, it will be plus. So it will be a minus here. Okay. So just check it. Oh, no, it's okay. It's plus. Sorry, it's plus. It's okay. It's okay. So there is no problem. So what is omega 0 I? So I can put it as minus omega. Clear? Huh? Okay. So you can write it as e raised power minus omega by 2. Okay. Alpha 1 gamma 0, like this thing. Clear? Now, any idea? So now let's take this gamma 0 here. So I know this alpha 1 and gamma 0, they anti-commute. If you remember, it is like this thing. Alpha I beta plus beta, alpha I that's equal to 0. Okay? So you are having an operation that's in operator that's in the exponential, is it? So you need to expand this thing. Let me show you. Most often, okay. So you can do directly. So you anti-commute them because it's alpha I. Once you take it on this side, it will give me a minus sign. But that minus sign will appear in the exponentials. Clear? Samajh aao? Okay, let me show you. So you are having e raised power minus omega by 2 alpha 1. How I will write it is 1 minus omega by 2 alpha 1, okay, then plus omega square by 2 factorial alpha 1 square plus 1. Sorry, minus will be next term. Okay, so let's write e raised power minus omega by 2 alpha 1 multiplied by gamma naught. So what it will be? It is gamma naught. So you multiply it minus omega by 2 alpha 1 gamma naught plus omega square by 2 factorial alpha 1 square gamma naught minus dash dash dash. Clear? Okay, so now let's anti-commute. Since alpha and beta anti-commute, so when they anti-commute, what they will yield me? Minus sign. Okay, so it will be minus gamma naught alpha 1. Clear? So what it will be? It will be actually plus. Since there are how many alphas? Alpha 1, gamma naught. So this will give you the minus gamma naught alpha 1. Then it will be gamma naught, so it will be plus. So the odd number of factors will yield you the minus sign, and even numbers will yield the plus sign. Ultimately, you will get gamma on the left. Clear? So that gamma naught I will take out. So what remains? 1. So this minus and minus becomes plus omega by 2 alpha 1 plus omega square by 2 factorial alpha 1 square plus dash dash dash. Okay? So what is that? E raised power omega by 2 alpha 1. Clear? Got it? So now once you anti-commute this thing, where the minus will appear? Here. Everybody followed it?
Yes, sir.
Okay, good. So therefore I can write this object as gamma 0 e raised power omega by 2 alpha 1. So how much is that? Gamma 0 square is equal to identity. It is equal to omega by 2 alpha 1. Okay? Okay, so now tell me how I can write this thing. Anybody? What is this objective? What is this that objective? This is actually SL inverse. Is it? Okay, now look here. So what is sigma 01? It's I alpha. I and I is plus. Clear? So it's alpha by 2. What is omega 0? Minus omega. So it's minus omega by 2 raised power minus 1. Clear? Got it? Everybody followed it? Okay, so what we have arrived at? So therefore, so we have this very identity at hand. Gamma 0 SL dagger, gamma 0 that's equal to SL inverse. So it means this very object, it will take the dagger of this entire object, so it makes it inverse. So you can define the inverse transformation from this dagger or the unitary condition using these gamma naught matrices. Samajh aa? Everybody followed it? Huh? Any question? So look here, what we have done. So we have started with the rotations and we have seen rotations form a unitary transformation. Clear?
Yes, sir.
But Lorentz-Bosch itself does not form unitary transformation. Clear?
Yes, sir.
Okay? So then what we have done? We have used this gamma naught matrices to get the unitary transformation back. To make this SL to be unitary transformation. How you can put it? So you can write it as gamma 0 SL gamma 0 whole dagger. Can you put it? Can you put it? So gamma 0 dagger, it will come here, then SL dagger, then gamma 0 dagger. Is it? So it will be the same thing, because gamma 0 dagger is Hermitian. So gamma 0 dagger is same as gamma 0. Clear? So that's equal to SL inverse. In other words, this object has a inverse like this thing. Clear? Samajh aa? So you can do it similarly for, let's say in general you can write it as, if you are having S inverse, so in general, okay, so you can write this gamma 0 as S dagger and gamma 0 in general. Okay, what is our S? So that's actually equal to gamma 0 e raised power, okay, S is minus, so it's I by 4 sigma mu nu omega mu nu gamma. Clear? In general, this can be done. Okay? Got it? So this is our S is our e raised to power minus I by 4 sigma mu nu omega mu nu. You can show it. Huh? Okay, so for this Lorentz boosts, we have shown it. For what I need to show it? For rotations, clear? So much, yes, for rotations. So what you need to do, you need to check what is the commutation between this sigma ij and gamma 0, and the commutation is equal to 0. So gamma 0 commutes with sigma ij, but gamma 0 anti-commutes with sigma 0 I. Clear? So because sigma 0 I simply gives you alpha matrices, alpha and beta anti-commute. Clear? And gamma gives you what? Sorry, the sigma ij gives you, it gives you what? What it gives you? So it gives polyspin matrices on the diagonal, is it? You remember it? So it gives you the spin, spin operators, and that commutes with this gamma 0. And gamma 0 is actually identity. Okay, one diagonal with the identity mat, another diagonal with the upper side with the 1 and lower side with the -1. Okay, so it commutes. You can think it simply as the identity matrix. Got it? Oh, samajh aa? Okay, check it. So you are supposed to check this object to be what? Equal to 0. Clear? So this is a very important relation, you should know it. Okay. So there is one another identity. Let's see. So you are having this gamma mu. Okay? So let's take the diagram of this and multiply gamma naught on both sides. What it yields? Let's take this identity. These are very important identities. You need to understand them. Huh? Okay? So what it will yield? Let's take mu equal to 0. Okay? So what it will give me? Gamma 0, gamma 0 dagger, gamma 0. How much is that? So it is gamma 0, gamma 0, gamma 0. What is gamma 0 square? That's 1. That's equal to gamma 0. It means gamma 0 dagger, gamma 0 is same as gamma 0. Clear? Okay. So now let's take mu is equal to I. So and I is so that's equal to 1, 2, 3. So how much is that? Gamma 0, gamma I dagger, gamma 0. So how much is that? Gamma 0. What is gamma I dagger? Minus gamma I, gamma 0. Clear? Okay. So now what is this? Gamma 0, gamma I, gamma 0. Since I is not equal to 0, is it? So gamma I is simply what? Alpha is, and gamma 0 is beta. So alpha and beta anti-commute. Clear? So that means if you take this on this side, so it's minus gamma 0, so it's minus gamma 0, gamma I. Clear? Yes, the anti-commute. What did you get? So gamma 0 square, gamma I. So that's simply gamma I. So it means what you get here. So gamma 0, gamma I dagger, gamma 0 equal to gamma I. So this is the generalization of your Hermitian condition, because gamma I are not Hermitian, but this kind of product makes it Hermitian. Okay? So therefore I can write this as gamma. Okay? Got it? Any question till now? Okay, so based on this thing, let's try to figure out. Okay, so what we have figured out, let's summarize everything. So we have got actually a transformation matrix under which a Sipner transforms in a well-defined way. Clear? Now let's check how different kinds of quantities will transform if I apply this Sipner transformation. So let's say if you are having a Sipner and you make a Sipner to transform in the in certain way, and you need to check how the different operators will transform under this transformation. Clear? Okay, so let's take an example first. So let's go to the continuity equation. So you are having this partial rho by partial t plus del dot j, that's equal to 0. Clear? So let's take the continuity equation. So what is our j? So rho, that is psi dagger psi. And what is this j? It is c psi dagger alpha k. Okay, so let me take kth element alpha k psi. Is that true? Okay, so let's put it in the 4-dimensional notation. Okay. So let me define this as, okay. Okay, so this way. Anybody? Can you tell me? So let me define an adjoint signal. Okay, so for the time, let's take the adjoint signal psi bar. This is the definition. This is defined as psi dagger gamma naught. Clear? So let's check actually the transformation properties of psi dagger first. Okay, so let me take the psi dagger first. Then you'll understand why I need actually this adjoint signal. So let's take, okay, so our psi goes as psi prime x prime as s psi of x. Clear? So this is our transformation rule. Now let's take the dagger. So how the dagger will go as? Anybody? So psi dagger will go as, you need to take as the dagger of this very object. Clear? Got it? You need to take the dagger of this thing. How much is that? So it is psi dagger of x and s dagger. Clear? Okay. So we have seen now s dagger is not equal to s inverse. Is that true? You got my point. S dagger is not equal to s inverse. Okay, what makes it s inverse? Huh? Using the gamma matrices. Clear? So what I will write it as, okay, so I will put it in this fashion. Okay, psi dagger gamma naught s dagger. Can I write it?
Yes, sir.
Okay, so what I will get? Am I doing correct things? Okay. Okay. So what is our definition? Gamma 0 s dagger gamma 0, that's equal to s inverse. So what gives me? So it is gamma 0 s dagger, that's equal to s inverse gamma 0. Clear? Is it true?
Yes, sir.
गड़बड़ मत हो। Okay, so I'll get like this psi dagger gamma 0 this way. What this object is? So it is S inverse gamma 0. Clear? Got it? So now, so what I will do? So I will take this gamma 0 on the other hand side. I will write like this way, or this psi prime x prime dagger multiplied by this gamma 0, it transforms this way, gamma 0 s inverse. Clear? Got it? So and this object I call as like this thing, psi bar s inverse. So this will be psi bar prime x prime. Clear? Got it? You got my point? So what is the reason behind it? Why we need to define this kind of signer? I mean psi bar, which we call the adjoint signer. So I will give the reason. Okay. So now let's take the probability density. So that's equal to psi dagger psi. Clear? So usually it is a scalar quantity. So if I make a kind of transformation, let's take, if you are having a scalar quantity, forget about this for the time being. So you make a coordinate transformation. Scalars remain as scalars. They remain invariant under a given coordinate transformation. Now since my probability density is what? It's a scalar quantity because it is the magnitude of the probabilities. It is psi 1 mod of psi 1 square plus mod of psi 2 square, and it's actually it's a scalar quantity. Clear? But it does not turn out to be scalar under Lorentz transformations. This psi dagger psi is not what? A scalar quantity. I need to construct a scalar quantity, is it? For that matter, I need to define this psi bar. Okay, so let's check the transformation property of this objective. Let's take this psi, it will go as psi dagger prime, okay, x prime, so that is different, understood? So let's write it. Okay, so what is psi dagger prime? It will be simply psi dagger, then s dagger. Clear? What is psi prime? It is s psi. Is it? So, but I know s dagger is not equal to s inverse. So, samajh? So that means this is not equal to what? Psi dagger psi. Since what is s dagger? Okay. So this identity holds for the inverse relation. Clear? Got it? So samajh? So it means this psi dagger psi does not transform as a scalar quantity. Now let's check the properties of the psi bar. So if I am having now psi bar of x and psi of x, so it will transform as, okay, so psi bar prime x prime, psi prime x prime. How much is that equal to? Okay. Okay. So what is psi bar? So it is psi bar s inverse, and psi is what? S psi. So what is s inverse s? That's identity. It is psi bar equal to psi. So it means this very objective psi bar psi transforms as a scalar under Lorentz transformation. If you make a similar transformation by x, okay, so it is the quantity psi bar psi which transforms as a scalar. Clear? So you see this kind of scalar I have constructed from two Sipners. Okay? So psi and psi bar. Clear? So we call these the quantities which have a particular transformation rule under Lorentz transformation as the bilinear Sipners. Clear? Or bilinear invariants. So this is a one type of bilinear invariant. Clear? Got it? Okay. So psi is sometimes this psi is sometimes known as bisipner. Okay? Because it comprises of four components. Okay, two components we can think corresponds to the particle, and other two components corresponds to antiparticle. Clear? So you are having a Sipner representing a particle, a Sipner representing an antiparticle. That's why you call it as a bisipner. So forget about, I will not use the terminology bisipner, I will be simply using what? Sipners. These are Sipners. Clear? So now let's look at this current density. Okay? So I will define my current density. J mu is equal to C times rho and vector J. Okay? Clear? So I will use this thing, and where J mu, so that's equal to, so I will write this J mu is equal to psi bar gamma mu psi, and there will be a C here, right? So now let's take J0. Let's take J0. If you take J0, it will be gamma 0. What is gamma 0? So, sorry, it will be like not psi dagger, it will be psi bar. Okay? So J mu is defined this way. Now let's check it. So let's check. So let's take J0. What is that? C psi bar gamma 0 psi. So how much is that? Psi bar is actually psi dagger gamma 0 psi. How much is that? C psi dagger psi. What is that equal to? C times rho. Okay? The first one. This is J0, huh? C rho, and rho is psi dagger psi. Now let's take J kth element. It is C times psi bar gamma k psi. Okay, so how much is that? So it is C psi dagger gamma naught. Okay, so gamma k psi. So how much is that? What is gamma naught? So okay, so this is actually beta, is it?
Yes, sir.
So let me write it. C psi dagger, it is equal to beta. So what is gamma k? It's beta alpha k. Clear? So how much is that? Beta square is 1 psi dagger alpha k psi. Clear? Okay? So now let's check the transformation of this J mu. So what exactly, how it transforms under this kind of transformation. Clear? Okay, so let's take, so you are having this J mu. Okay, so it will transform as J mu prime. Let me write J prime mu. So that's equal to, okay, since we are using C equal to 1, so let me take C equal to 1. So it is psi bar prime x prime gamma mu psi, okay, prime x prime. How much is that? What is psi bar? So it goes as psi bar S inverse, then you are having gamma mu, okay, so it goes as S psi x. Clear? So now tell me, so we have this identity for Lorentz transformation. So lambda mu nu gamma nu, that's equal to S inverse gamma mu S. Is it? So this is the identity we have already derived. Okay, so now let me use that. So it is equal to psi bar. What is this now? So it's lambda mu nu, okay, gamma nu psi. Clear? Okay. So how much is that? So you can take this lambda mu nu psi bar gamma nu psi. So what this object is? This is J. So it is lambda mu nu J nu. So what is the transformation rule? It is the transformation of vector. Okay. So how a vector transforms under Lorentz transformation? X goes as x prime mu is equal to lambda mu nu x nu. Is it? So is this the transformation rule for the okay? So this is how a 4 vector transforms. So that means this J mu transforms as a 4 vector under Lorentz transformation. It's a vector. Clear? Got it? समझ आया? Okay. So let's do it in a general fashion. Okay. So now let me introduce another kind of matrix. Okay. So let's define. So its importance will come. I mean later in the course. Okay. So let's define. Okay, gamma phi, that is same as what we call as this thing. It's I, gamma 0, gamma 1, gamma 2, gamma 3. So let's define another gamma matrix, what we call as a gamma phi matrix. It's sometimes known as chiral matrix. Okay? Clear? So this matrix has its importance when we take the parity transformations in a given interaction. Okay? Clear? So gamma phi, this is how we define it. Okay? So can anyone tell me what is the value of this gamma phi? If you multiply this gamma 0, gamma 1, gamma 2, gamma 3, gamma. Okay. We are so what it would be? What it would be? Huh? No, what it would be? It turns out to be like this thing. An identity is 0, no. So let's multiply. Let's multiply. So it's I times, what is gamma 0? Huh? No, what is gamma 0? It's I 0 0 minus I. What is gamma 1? 0 sigma 1 sigma minus sigma 1. 0, is it? So what is this thing? 0 sigma 2 minus sigma 2 0. Okay? So then what you are having? 0 sigma 3 minus sigma 3 0. Okay, so what is the, I use it here a representation where gamma 0 is diagonal. Okay?
Yes,
I am calculating this gamma 5 in terms of the diagonal representation of the gamma 0. So you need to multiply them. Huh? So let me check what is the value. It's like this thing. I think it will be an identity matrix. Sorry, like this thing. Identity, identity, and 0. Okay? So you need to check it. Huh? No, it is not like this thing. So let's calculate it. Let's calculate it. Okay. Okay, so calculate it. So what this is? So you are having this 0. Okay, so I is there. So it is 0. Then what you are having? Sigma 1. Okay. So this multiplied with this thing is 0. Then you are having sigma 1. Then what you are having? Sigma 1 here, 0. Clear? So let's multiply. So it is minus sigma 2, sigma 3. Then you are having 0. Then you are having what? 0. Then you are having minus sigma 2, sigma 3. Clear? So now let's multiply. So it's equal to 0. Clear? So what you are having there? Okay. So it is minus sigma 1, sigma 2, sigma 3. What you are having there? Minus sigma 1, sigma 2, sigma 3. Then you are having 0. What is the product of these three? What is sigma 1? Okay, so there is an I sitting here. What is the product? It's actually equal to minus I. So what is sigma 1? So it is 0, 1, 1, 0. So let's take, then you are having 0 minus I 0, then you are having 1, 0, 0 minus 1. Now let's calculate it. There is no round, so it is I, this will be 0, this will be 0, and this will be minus I multiplied by this thing. Okay, so 1, 0, 0, minus 1. Now let's calculate it. So it will be equal to I, 0, 0, and it is I. Okay. So how much is that? And there is minus already sitting. So it is minus I. Eh? So it's like this thing, I into minus I, 0, 0. So 0 minus I, 0. How much is that? So it is 0, 1, 1, 0. Okay? Clear? So we are choosing a representation where gamma 0 is diagonal and gamma 5 is having the value. Gamma 5 is now equal to 0, 1, 1, 0. Clear? Got it? Now there can be a representation where you can choose gamma 5 to be diagonal and all these gammas are non-diagonal. Clear? Got it? So much, Yaman? Okay. So now let's take, for the time being, gamma 5 is having this kind of matrix. Clear? Okay. So now how many gammas we are having at hand? Okay, we can construct out of these gamma matrices how many? Okay. So we are having this identity matrix. Okay. So we are having a set of gamma matrices. Clear? Out of these gamma matrices, we can construct the following set of gamma matrices. Clear? Okay. So we can be having now gamma 5 as a. We can have this gamma mu, we can have this gamma mu, gamma 5. Can we have? So we have constructed these from gamma matrices, clear? And we can have another matrix like sigma mu, clear? So how many are they now? Okay, so this is 1, this is 1. How many? 2. So 1, 1, and how many they? 4. This is again 4 because mu goes from 0 to 3, is it? So you are having now how many? 1 matrix, 1 matrix, 4 matrices, 4 matrices, and how many they? 6. So how many total? So you have constructed actually 16. So these are actually 16 linearly independent matrices. Independent gamma matrices. Clear? So it forms a 16 dimensional basis. Clear? Okay. Okay. So we can construct using these 16 gamma matrices. Okay. So this kind of set of matrices, we can form different kinds of objects. Clear? So now let's take the first object. Okay. So we have constructed actually the psi bar identity. Psi. What is that? Psi bar psi. Clear? Is that true? So let's call this as this set of matrices as gamma. This capital gamma. Clear? Okay. So we can construct using these gamma matrices these kind of products, and we need to check how they transform. We can construct in general psi bar gamma and psi. This kind of product we can construct in general. Clear? Clear? Okay, so this kind of product will have a definite, transformation rule under Lorentz transformations. Clear? They will transform in a certain way under Lorentz transformations. Clear? And we call this kind of product as a bilinear invariant. Clear? Bilinear invariant, in a sense, they will have actually a well-defined transformation property under Lorentz transformations. Okay, or these Simpson transformations. Okay, so now let's take the first one, where this gamma is identity. Clear? So this identity belongs to the set. Clear? So what is that? Psi bar. Psi. We have just seen it is same as what? So you are having psi bar prime x prime, psi prime x prime. This is same as what? Psi bar x and psi x. So when you are having the quantity same as itself under Lorentz transform, what we call it as? So it is a scalar one. So that means this object transforms as a scalar. Clear? So it is a Lorentz scalar, I can say. Huh? Got it? Now let's take another quantity. This thing. Okay, psi bar gamma mu psi. We have just seen it. Okay, in terms of J. Clear? So how it transforms as? So this goes as psi bar prime gamma mu psi prime. This we have just seen as lambda mu nu psi bar gamma nu psi. Clear? So what it is? It's a vector. Okay? Because J we have shown a vector. So J is essentially this object. Yeah? So it is a vector. Clear? So that it's a 4 vector. Eh? It transforms as a 4 vector. Now let's take this object. Then I will take the gamma 5 kind of business. Eh? Okay. So now let's take this psi bar sigma mu nu psi. Let's take this kind of thing. Eh? Clear? So this is very important. You should know these kind of transformation properties when we will describe interactions. Eh? Because fermions interact in a different way. Eh? Okay. So different kinds of interactions are there. So let's take. So it goes as psi bar prime sigma mu nu psi prime. Clear? So what is that equal to? So it's actually psi bar prime. What is sigma mu nu? It's I by 2. Okay, so it is gamma mu minus gamma mu psi prime. Clear? Sigma mu nu is like this thing. Yeah? Okay. So what is that equal to? I by 2. So let me take only one quantity, one term. So you are having psi bar prime gamma nu psi prime minus mu and nu are interchanged here. Right? So if you look at the second term, there are mu and nu interchanged. Okay. So let's take it. Okay. So what you are having? So it's equal to, okay, I by 2 psi bar prime. So it will be psi bar S inverse, then you are having gamma nu, and psi prime is actually S psi. Okay, minus like this. Clear? Got it? Now tell me, so can I write it as I by 2 psi bar? So I will write it as S inverse gamma mu S, then S inverse gamma nu S. Can I write it? Can I write it? So I have just introduced what? An identity. SS inverse is 1. Huh? So now what this object is? Anybody? So it is I by 2 psi bar. It is simply lambda mu. Okay, nu there sigma. So let's write gamma sigma. Then this will be lambda nu. Oh, okay, rho gamma rho psi. Clear? By the definition of, okay, so this is the definition we are using. Okay, lambda mu, okay, gamma nu is equal to S inverse gamma mu S. So we are using this definition, okay, minus mu interchange. Clear? So you have, now you can take this lambda mu sigma out, lambda nu rho out, what remains there? Okay, so this psi bar, I by 2 gamma sigma, okay, gamma rho, okay, clear? So now when you interchange mu and nu, so it will be actually sigma and nu interchanged, minus like this. Clear? So what is that equal to? Lambda mu sigma, lambda nu rho, so it is simply psi bar sigma rho psi. Clear? Got it? Huh? So this is simply the other term that I have. So there will be rho and sigma will be interchanged. Clear? So it is sigma. So what are these things? These are two matrices. So it transforms as a tensor, rank 2 tensor. Clear? So it means this very object is a tensorial quantity. It transforms as a rank 2 tensor. Clear? Now let's look at the gamma phi. Okay? What is gamma phi doing? Okay, gamma phi is used when there is a parity involved. Okay, you should know. Parity means if you take, let's say, x to minus x, clear? So parity means what? So I will do it in detail. Parity means you take an vector from, you just reflect it about origin. Clear? So let's do it. Here we'll discuss parity. Or maybe in the next lecture, let's check.